Hello and welcome to another lecture session of Introduction to Astrophysical Fluids. In this session, we will discuss a new topic, which is the topic of astrophysical dynamos. Evidently, this is going to be the last topic of this course. Okay. To be very honest, in the scope of this course, I can only present you less than 1% of the whole picture of the astrophysical dynamos. Okay. What I would try to convey is the necessity of a dynamo theory and in which sense we can apply dynamo theory to sun, earth or galactic magnetic fields. Okay, so once again I will not be emphasizing much upon the mathematical rigor, rather some qualitative discussion and the conclusion of some theorem or some theory without doing the mathematical development, the proper analytical development will be conveyed in this lecture. Okay, so for the first time it was Gilbert who was actually by profession a physician of Queen Elizabeth. Okay, first Elizabeth, of course. He announced or he suggested around 1600 that Earth is a huge magnet. Okay, and that was the first time that someone suggested that Earth has some magnetic property on its own. And he actually suggested that while explaining the directional properties of the magnetic needles or compass on Earth. Okay. Now, at the very outset, people thought that okay, the Earth core is consisting of nickel, iron, this type of ferromagnetic metals. So due to this ferromagnetic core, maybe we can have this magnetic property. So this was totally at the first hand it looked somehow very reasonable. But by the end of the 19th century, people, when they came to know about phase transition, magnetic phase transition, and the existence of a point or the temperature called the Curie temperature, then they realized that the temperature in the Earth's interior was much greater, and actually is much greater than the Curie temperature of all ferromagnetic materials possible. And that means that in the Earth's interior, all these ferromagnetic materials can actually behave or actually would behave like a paramagnetic material that you all know from your knowledge of Curie point. Okay, so that's why this explanation that the Earth's magnetism is due to a ferromagnetic origin, ferromagnetic origin due to the ferromagnetic materials at the Earth's center was discarded. Now actually then explanation was due for the terrestrial magnetic field. Now the terrestrial magnetic field is in a sense weak, moderately weak. This is of the order of 0.5 Gauss, okay, to 1 Gauss. As you know that 10 to the 4 Gauss make 1 Tesla. So this means it's almost of the order of 10 to the minus 4 Tesla. Okay. Now, as you know that in laboratory magnets, in general, you can have magnetic strength from 0.01 to 0.1 Tesla. Okay. So with respect to that, Earth's magnetic field is quite weak. Now, in 20th century, astronomy had a remarkable progress, and that actually confirmed that magnetic fields are not only something which is a property of the Earth, rather it is ubiquitous in nature, in astrophysics, in galactic physics, I mean in the galactic domain. So Earth, Sun, stars, intergalactic medium, etc., etc. Okay. Now, other than this terrestrial magnetic field, three instances are of very much interest. That is the solar magnetic field, because that's what Hale in the year 1908. I already have discussed this person, Hale, 1908. Okay. So while discussing about the sunspots, so he, for the first time, he concluded about the sunspots to be the region of extremely strong magnetic field. Okay, and actually the solar magnetic field in the near the sunspots, they are of the order of 10 to the 3 Gauss. So this is almost like the magnetic field of normal laboratory magnets, and even for the larger sunspots, this can go up to 5000 Gauss. So it's a moderately strong magnetic field. It's not very strong magnetic field, but moderate magnetic field. Okay. Now another thing is the pulsars. We already have talked about pulsars while discussing the rotation. Okay, the effect of rotation in astrophysics. Pulsars are the rotating neutron stars, and these pulsars have a very, very strong magnetic field, which is of the order of 10 to the 12 Gauss. Now you can understand 10 to the 12 Gauss. This means 10 to the 8 Tesla. Oh, it's enormous. Okay. Then another, so this is one extreme. This is one borderline. The other borderline is the magnetic field of the spiral galaxies. That is 10 to the -6 Gauss. Very weak. But still it has a magnetic field. So we see that terrestrial magnetic field, solar magnetic field, pulsar magnetic field, and spiral galactic magnetic field. 4 cases are of very, very interest in the astrophysics. Now, first of all, since we are from Earth, we are the representatives of Earth, and we are in the solar system of Sun. Sun is our, the head of the family, of solar system family. Then we will be interested first in the comparison of solar magnetic field and Earth's magnetic field, just for information. So solar magnetic field is periodic and actually varies as a wave-like fashion in time, and actually it flips its direction in every 11 years. But on the other hand, Earth's magnetic field is very much static, and it actually flips very occasionally. So, till now, for example, after our astronomical and scientific progress started, Earth's magnetic field never flipped. So it was conjectured that in the past maybe it flipped, but very occasionally. Okay. Now, whatever be the model we propose for the astrophysical magnetic fields, for the origin of the astrophysical magnetic field, because that is the question of the central question of the core, that why there should be a magnetic field in this Earth or Sun or any other systems where we know that the normal ferromagnetic origins are discarded to be the cause of those magnetic fields. Then we have to think of several models, of course. Now, whatever be the model should, or rather must, satisfy all the known features of solar and terrestrial magnetic fields, right? So it should be, in a sense, if we want to propose a general theory of the astrophysical and interstellar magnetic field, then that should also include the solar and terrestrial magnetic field as well. If it is a general theory, it should include so that should be able to explain the origin of the magnetic field from our planet to the spiral galaxies. Okay, that's very straightforward claim. But before looking for a model in order to explain the terrestrial and extraterrestrial magnetic fields, let us first understand why we cannot model just by a hydrodynamic model of plasma with B is equal to 0. So that is the question. So why we are claiming that all these models should have some magnetic field, and that's what we are searching for. I mean, why just we can simply say that, okay, we have a plasma, we have a plasma, but the plasma has a magnetic field which is 0. Okay, and so this plasma should have some electric field maybe, but its magnetic field is 0, so it's a hydrodynamic, it looks like a hydrodynamic fluid with magnetic field equal to 0. Okay, in the at least in the case of so electric field is non-zero, but electric force is 0. So finally the total system should behave in a monofluid framework. The total plasma should behave like a hydrodynamic fluid. Why this is not possible? Well, of course, the first point is that by observation we have already found that there are strict evidences of magnetic field in various cases, as I just mentioned. Another thing is that even theoretically, in several circumstances, B is equal to 0 state of a plasma leads to an instability. And that instability, what happens, that leads to the growth of some statistical fluctuations of magnetic fields, which is called the seed field, seed magnetic field. So seed field, which comes from the statistical fluctuation of negligible magnitude in general. But due to that instability, okay, even if you model the plasma with B is equal to 0, actually it will never remain or retain its stability with B is equal to 0. So it will tend to such a condition where the very small statistical fluctuations of magnetic field which were neglected in general now would lead to some stronger considerable magnetic field of large scale. And this is known as the hydrodynamic dynamo process. Now, why the word dynamo comes here? Well, from lexical meaning we know that dynamo is something which is exactly opposite to a motor. So yeah, in a motor you give electric energy and you out of that electric energy you consume electric energy, you make some mechanical work. Okay, on the other hand, for a dynamo you supply mechanical work, and using the very basic principle of the electromagnetic induction, simply it creates a situation where you have a variable flux situation, and that's why finally it creates an EMF or electromotive force, which thereby leads to a current. Okay, and actually another very straightforward way of saying is that you give mechanical energy as input and you take or you have electromagnetic energy converted electromagnetic energy as an output. So conversion from mechanical energy to electromagnetic energy is a very simplistic way of explaining dynamo. Okay, now the question is it something similar which is happening here? Because we have till now what we have said, we cannot see anything like we are giving some mechanical force or something mechanical energy and electromagnetic energy is converted. Well, of course there is something similar. Okay, but before going to that question, let us start by saying that what happens if the magnetic fields of the sun or the earth or the galaxy can be explained by some dynamo action. Okay, of course, if this can be done, then everything is solved. Okay, that means that the ferromagnetic theory is no longer there. Now if the dynamo action is can be used to explain this, that means that you are giving some sort of mechanical energy to the system, or the system takes some mechanical energy from some source, and the system in response creates some current, and that's why some magnetic fields, because you know by Maxwell's equation, magnetic field, in the situation for non-relativistic MHD where you neglect the displacement currents, so you have normal free current. Okay, then you can actually write curl of B is equal to mu naught J, and then your simple current means a magnetic field. Okay, so in this way people started to think. Now let us once again, in order to approach this problem, we have to start from some point which is very simple, and then we will try to sophisticate step by step. So let us first neglect, for instance, the plasma motion inside an astronomical body. So one thing is very clear, that the plasma cannot have B is equal to 0, because once even if you make B is equal to 0, just by the fluctuations in B, the statistical fluctuations which are inevitable in a realistic plasma, will always tend to a condition where you have a large scale large scale plasma, strong magnetic field. Okay, now let's say you have a magnetic field, but inside the plasma, inside an astronomical body, what happens, that the plasma motion is very negligible. So you can practically claim that the plasma velocity is almost equal to 0. So if the plasma velocity is 0, then the momentum evolution equation doesn't have any meaning, and the only evolution equation for the magnetic field is nothing but the induction equation. But again, the curl of V cross B term would vanish because V is 0. Then effectively your magnetic field, which is now created by some instability, okay, from some seed magnetic field, would simply diffuse with time. Okay, and the characteristic time of that diffusion can be simply calculated from this type of estimation. Okay, so you can see here, so from this equation you can write, I can simply write that this is equivalent to B by some characteristic time tau, just a minute, eta B by some characteristic length square. So then tau should simply be equal to length scale square by eta, where eta is the magnetic diffusivity. Okay, and then if you calculate this thing using certain process, which I am now going first to describe, that first the way of calculating eta is, so eta is related to the conductivity, because in this case we are all talking, because of the standard techniques in standard practice in astronomy, we express the quantities in CGS units. So if you know this conductivity in CGS unit, then eta, or the diffusivity, will simply be equal to c square by 4 pi this conductivity. Okay, and this conductivity can actually be calculated as, in CGS, 10 to the power 7 times the temperature to the power 3 by 2 of that medium. So now if we take the earth if we know the core temperature of the earth, okay, or the temperature of the earth's core, or the temperature of the solar like sun, or the solar plasma, or the temperature of the galaxy, okay, then we are done. Now taking, for example, solar and galactic temperatures to be respectively of the order of 10 to the 7 and 10 to the 2, we can calculate the corresponding sigma. Okay, now it is a very small task for you. What can be the temperature of Earth's core or the Earth's central part, in order that sigma, which we know for Earth, is giving something which is sorry, not exactly this. Is simply c square by 4 pi into 10 to the 16, because sigma's value in for Earth is 10 to the 16 ESU. So my question to you is that if sigma is 10 to the 16 ESU, then what is the temperature of the Earth's core, the estimated temperature? Okay. So now this is actually very known, and that's why we use this formula, I mean value for sigma, and we use this formula over here, thereby getting eta to give us such a value such a value which leads to tau to be 3 into 10 to the power 5 years. Now here if you calculate eta, and then if you just take the L, the length scale, to be of the order of 3 into 10 to the power 8 centimeter, that is nearly 3000 kilometers, which is roughly of the order of the radius of the, half of the radius of the Earth actually. Okay. So then you can simply calculate from this one and from this one the tau in seconds, and finally you have to convert this into years, and finally you will have the tau, or the relaxation time, or the decay, characteristic decay time for the magnetic field, decay by diffusion, okay, is 3 into 10 to the power 5 years. Now this time is of the order of 10 to the power 11 years for the Sun, and this is 3 into 10 to the power 23 years for the galaxy, actually the spiral galaxies. Okay. Now it's true that so these three characteristic times are very important, because depending on that, now we will discuss some specialities or some facts about all these three type of magnetic fields. Okay. Just for information, that when you will try to calculate tau for Sun and galaxy, just take their corresponding length scales as 5 into 10 to the power 10 centimeter, and for galaxy 3 into 10 to the power 20 centimeter. Okay. And then this is a small home task for you to calculate the tau for Sun and the galaxy, and to check whether we agree or not. Okay. Of course you have, that should be in agreement. Okay. Now interestingly, a very strange fact for Earth's magnetic field is that the Earth's magnetic field has already lasted. That can be done in other ways. Okay, that I am not entering now. This has lasted for more than 3 into 10 to the power 5 years with a very considerable value. So this is not really following this equation then. So there is something in addition to this which actually counterbalances this diffusion. Okay, or the decay by diffusive effect. So there must be some mechanism to sustain the terrestrial magnetic field. So that is first necessity. Now for Sun, the problem is that there is no problem with the decaying time, but because the Sun's corresponding characteristic decay time is 10 to the power 11 years, and that is completely the Sun's magnetic field is well within, but the problem is that the Sun's magnetic field is oscillatory, and magnetic field actually flips every 11 years, whereas its diffusive decay time is 10 to the power 11 years. Okay, so we have to also find some mechanism in order to explain the oscillatory nature of the solar magnetic field. Finally, for galactic magnetic field, similarly, some mechanism is needed to prevent the winding up of the magnetic fields due to the differential rotation of the galaxy. Now, for the galaxy, this is not a problem of the diffusive decay is not a problem, because 3 into 10 to the power 23 year is much larger than the age of the universe. That's completely okay. So there is no doubt that the galactic magnetic field cannot decay in by present time, okay, just by diffusion. But there is, in spiral galaxies, there is considerable differential rotation which can wind the magnetic lines of force and thereby destroying them. And that is not possible if we have a mechanism which sustain the magnetic field, so that the magnetic fields of the spiral galaxies are actually always acting along the spirals. And that's a very famous thing. You can actually see several images that the magnetic, for a spiral galaxy, the magnetic fields are actually directed along the arms of the spiral. Okay. So all these above said points finally indicate that magnetic fields need to be continuously generated by a process, and which is likely to be the dynamo process. Okay. Now, it is true that now we come to this question that why this is called dynamo, because when we are talking about a dynamo process, we are talking about plasma, and the blobs of plasma, in case where you have the dissipative effect to be negligible with respect to the curl of V cross B term, then you can actually write the effective induction equation like this, and then you have your for your plasma magnetic frozen in the frozen in field theorem for magnetic field to be approximately true. And if this is true, then this simply says that the blob of plasma, okay, has some velocity lines because this is moving, and this simply drags the magnetic field lines, okay, due to this frozen in field theorem, because the magnetic field lines are frozen in the plasma, to produce an effective electromotive force, okay, because of the convective motions and irregular motions. So you can actually see that there should be they construct various situations where you can have a situation of changing electromagnetic flux, okay, and that creates an induced EMF just by the process of electromagnetic induction, okay, and that is the that is the source or the center, that is the basis of calling this whole process as a dynamo process. Okay, now we have to look for the mechanism of the dynamo action. Of course, we consider for simplicity an incompressible fluid, because compressible always makes the life a bit complicated. So for incompressible fluid, we will just see that how in a very simplistic way we can study the dynamo effect in it. That means once the magnetic field is generated from the once some considerable magnetic field is generated from some seed field, how can the system sustain it? And we have two equations in hand, force equation and the induction equation, because for incompressible fluid we don't care about divergence of V, divergence of B is equal to 0, and then we also don't care about the energy equation. But these equations are also not easy to be solved, because they are nonlinear coupled differential equation, as I just said maybe in the last lecture, that in general, the induction equation has this term curl of V cross B is equal to del B del T. So although it may look like this is linear in B, but V has a feedback of B and B has a feedback of V, so that's why the system is actually non-linear. Okay, but if we consider for the time being to start with that the velocity field is given by some process which we are not interested, and the magnetic field is just affected by that velocity field, the magnetic field's evolution, and the magnetic field's evolution does not give any feedback to the velocity field, then the induction equation is effectively linear in B, and then it is much more easy to solve. And so then this induction equation is known as the induction equation for a kinematic dynamo. Okay, the corresponding problem is known as a kinematic dynamo problem. Now, for historical reasons and for the sake of simplicity, we in general talk for academic purpose, I mean almost all the time in general in the introductory courses at least, the kinematic dynamo problem, where the induction equation is totally decoupled from the momentum equation, and the magnetic field does not give any feedback to the velocity through the Lorentz force. Okay, now in the in the next discussion we will discuss very briefly one theorem and one qualitative idea of turbulent dynamo, to see that how very simplistic, in a very simplistic way we can try to solve the problem. Okay, of course this will be done also in a very superficial manner. Okay, thank you very much.